like to go the second part. Okay, backpropagation. Let me take this as an example. Backpropagation is input X. It could be the 1, 2, 3, and there's a hidden layer. We still have a couple. This is the output. So output will be the something we try to predict. We're called the target Y. And the Y hat represents in terms of the linear combination, and this is the value of the node multiplied by weights, and combine them, and and also the bias is added, and do the nonlinear transformation by using the activation function. Then that renders the output that the Y hat used to predict what the Y should be. And so the error term of the output layer can be considered the delta 3, 1, 2, 3 equal to the A3 output minus Y. So in here, there's a delta, this is delta 3, and this is delta 2, and this is the error term of the hidden layer. And based upon the relationship, it can be solved by using the chain rule. Okay. So let me take the backpropagation example. That is more straightforward. Like we have two input node, 1 and 2i, hidden layer H1 and H2, O1 and O2 as an output. So there's a W1, W2, and W3, 1, 2, 1, 2, the 1 and 2, and this is 3 and 4, 5, 6, 7, and 8. So the B1 and B2 are placed in the intermediate as the BIOS. So first of all, look at the forward pass. So yeah, like this network, the hidden H1 is equal to the multiplication of the node times the weight 1, the I1 W1, I2 I2 W2, and plus the B1 in here, B1 here, B1 to here, to produce H1. And likewise, we like to H2 the H1 times the W3, and I1 times W3, and I2 multiplies the W4, and the plus the B1 to give the H2. So the output H1 right here, do the activation function that H1 as the operand within the parentheses, the output H1, and this output H1 times the W5, and output H2 times H6 to produce O1. W6 plus the bias 10 to produce to produce O1. And O2 can be generated in the same manner. So the total error, since the error could be positive or negative in order to cancel out to each other. So we like to evaluate in the square error. So the target I times the output, the target I, the output, take the square that. Then backpropagation in order to so when we evaluate, so the stochastic gradient descent, like to update W5, W6, W1, and W2. How can we do that? By the chain rule, expected value, since we got the result right here. So the best way just to go reversely from the end toward the star. So that's called the backpropagation. So the partial derivative expected value of the arrow total with respect to the W phi. W phi is right here. W phi is right here. Oh, I'm sorry. W phi. And equal to the partial derivative of the arrow of the output O1. Output O1 right here. Output O1 and output O1, which directly the net one is net O1 is right here. The net one, the network R1, the net one. And with respect to partial derivative, then net O1 W phi, O1 W phi, the O1 W phi, net one. The O1 net the O1 the O1 and the net O1 and well, so this apply the chain rule. So you can see that they cancel out each other, finally turning out to the partial derivative of total arrow with respect to W phi. So so the illustration is totally follow the chain rule. So with respect to this equation, we take the first derivative, partial derivative of the total partial derivative of the R1, the R01, and this by the chain rule, this is 2, and partial derivative R1, this is a -1, and multiply in here, the 2 times the 1 over 2, the -1, and the second is a 0, okay? So this is 0 right here. So after arrangement, there's the cancel out. This is the minus target 1 and the target 01, target 01 minus the R01. So if the activation function is taken by the logistic, so take the first, is take like this. So out the O1 is equal to the 1 over the parenthesis 1 plus the exponential minus the net O1. Then partial the R01 partial, the net one is equal to, yes, and is this one. So there's so 1 minus the partial 1, since the minus is right here, and the O1 times the 1 minus R01. So this is exponentially. Then since net O1 equal to the W phi times the RH1, there's a hidden layer plus the WX, the output of the hidden layer 2 plus the B2, the bias. So we can take the partial derivative, know the output 1 with respect to the wave 5. So W phi right here, take the y is the 1, this is the output H1. So this is nothing to do with the W phi, the 0, 0. So this is directly equal to the hidden one. Since then we can find the value partial derivative with respect to the total, which the arrow with respect to the W phi. So this is some value we would like to use in this equation. Then that is equal to the minus target, minus the parenthesis target O1 minus the output O1. And this is this value, the partial E, partial R01, partial E, partial R01, partial net O1. This is right here, partial R01 and partial net O1 right here, times a partial net O1 and partial W phi. That's equal to this. This is our H1. So know that the target O1 and our O1 and our H1 obtained from the forward propagation already. So we can see that the target is our O1 and our H1 and our H1. So they can be obtained. So this can be obtained, and the stochastic gradient descent can be formed. the W5T plus 1 equal W5T minus alpha is learning rate. A partial derivative, the total error of the W5 is right here. This equation. So it's a forward pass. It can be obtained. Okay. So this is with respect to the W5, and W6 and W7, they can be calculated in the same manner. Okay, then, so this is the backpropagation, how we take advantage that this is how the Jeffrey Hinton won the Nobel Prize in physics in 2024. So this is backpropagation in CNN. This is we just put in the CNN case inside of CNN. Compose a 2x2 filter Wij with a stride of 1. So each time F1, 2, 1, 2, 3, 4 times 1, 2, 3, 4, the W1, F1, F2, W2, F4, W3, F5, W4. So you can see that this W1, W2 with corresponding F1, F2, and the 4 times the W3, 5 times the W4. So we just convolve them to produce A1. So this is to A1, this is A2, this is A4, A3, and A4. So this is how the A's are computed based upon the linear combination. So we think of the F1, F2 to F9 are serious input. So this is a well-known node for the deep neural network. W1, 2, 3, 4 are shear weights. 1, 2, 3, 4. And that connect the A1, 2, 3, 4. So the backpropagation chain rule above can be applied to update the WI. So take the first derivative. So this source, there's some source you can find. So based upon this rule, and then with respect to the error, with respect to the weight can be computed based upon this relationship. So backpropagation chain rule above can be applied. And what else? So if this is possible, if this is possible and the CNN, that's all. So this CNN by the striding, by using the convolution, the update of the weight can be possible. Okay, then more activation function like a leaky ReLU. Originally, the ReLU is like this. After 0, they all 0. If this is if the horizontal axis smaller than 0, all the activation going to be 0. However, the leaky ReLU, so we take the maxima alpha x and the x. So the amount of leak is determined. So it's called the leaking by the value of the hyperparameter alpha. So if the value is quite small and generally varies between the 0.1 and the 0.1 or 0.2, 0.01 and 0.2, similar to the ReLU. The leaky ReLU is continuous everywhere, but in this point, it's totally indifferentiable. And it is non-differentiable 0, so the derivative of function is 1. Totally, this is 45 degree. And the alpha for s for the x is the smaller than and that is alpha is a 0.1. This is the alpha could be quite small, yes, like a 0.1. Slope is quite small, close to 0. Okay, so this is called the leaky ReLU. Exponential linear unit called ELU. Like this. This is exponentially increasing like 45 degree. However, less than 0 exponential, that's still increasing if the x start from the -5 and increasing up to the 0 and then there's a linear increasing. So mathematically, the ELU activation function can be written. So if x is less than 0, the -1, so the -1. So if the x is greater than 0, this is a 45 degree, and then the exponential x, the 0 is exponential is a 1 minus 1 is a 0. So if it is smaller than 1, so this is going to be the negative. So this is exponentially, still exponentially increasing. Then this is a graph for the ELU graph. So unlike ReLU, ELUs curve have a negative value right here, to which cause the mean of the ELU activation function shift toward 0. So the training of the model converges faster than the ReLU and is a variance. So yeah, typically with the leaky ReLU, so ELU could be another one can be considered. That can be considered. And then the next one, this is the one I like most, called the scale exponential linear unit, called SELU. If greater than 1, always a 45 degree, less than 1, the alpha times exponential x minus alpha. So this is SELU function with the alpha and the lambda is the shape lambda scaling parameter. The alpha is yeah, it's all the scale parameter. So you can see that when this is the constant, right? This is a 0.1, the 45 degree. However, if take the first derivative, it is increasing. So this is increasing. However, this is still non-differentiable with respect to the 0 point. Then this is increasing and constant, increasing and constant. So the alpha equal to the 1.05, the alpha, the scaling 1.6. So SELU activation function with alpha 1.6733. Alpha is equal to 1.0507 in the derivative on the right-hand side. The values above are used to preserve the mean and the variance of the input. So how can you say that of the input? So you can see that, so you can take the expected value of the, so you can the constant and it is still increasing. However, it is not that large. So keep the mean and variance of the input finite. This is finite. That means it converges. And the switch. So mathematically, it is defined as a switch x times the sigma and a function of the beta x. The is a sigmoid function involved, and sigma x is equal to 1 divided by 1 plus the exponential minus x is sigmoid function. So beta can be either a constant defined prior to the training process or parameter that can train during the tuning time. So beta can be, so this shape like this is a initially beta can be large and it is a monotone decreasing. Switch curve with a different beta, look at that. If the beta is quite small, you can see that it's like a straight line. If the beta is quite large, it's more curvature and then still close to the 45 degree. And CNN structure. CNN structure, typically it consists of the convolution layer, the number of filter that should be determined. What page? Okay. Then the number of filter, the filter kernel size, and the stripe, how you move the kernel, and the padding. Do you need to keep the original size of the feature map, and the activation? What kind of activation? Sometimes you can try. So to activation ReLU or the GALU, yeah, typical, or a second. You first use the ReLU or GALU, the second use a sigmoid or hyperbolic tangent, and finally ReLU. Pooling layer, pooling size, typically 2 by 2. The pooling type can be max and the mean or square root, mean square error. Or strike. Normalization, batch normalization, or layer. Typical batch normalization is required. If you like to apply the deep learning model to nonlinear, the natural language processing, the layer normalization layer is frequently utilized. And the flatten, not required for 1D sentences, already need to flat entire series and the computer softmax and assign to each class the output, each output of the class. So flatten and the dense layer, the fully connected number of the node, the fully connected, and this the flatten and activation function, the dense layer. Flatten, yeah, dense layer, the fully connected as well. Finally, things are flattened, going to the number of the flattened neuron got to be much, the number should much more than required, and the dense just condense the flatten a little bit. Finally, assign the softmax to each node of the class. That is the output. The dropout. The dropout should apply before the output node. So dropout probability typically use a 0.35 or 0.45, no more than 0.5. Typically I use a 0.45. Output layer, this is a dense layer, the number of classes of responses. If you like to use deep learning as a class for the predictions, the number of classes can be divided more meticulously, or the interval could be very small. That is a classification problem can transform into the prediction problem, like a card. The card classification card CART as a regression tree. Classification and the regression tree. Number of cards and activation as softmax. Then optimization, the loss function, what kind of loss function, cross entropy, or if you use this reconstruction error optimization algorithm, Adam typically utilize a batch size, number of epoch, and the run rate. So you can check every time you use that from the GitHub. You can check all the default hyperparameterized setting for each deep learning structure. And outline of the training program. Using these formulas, we can effectively write an algorithm train the network using a single training sample at a time. And however, the training size should be randomly sampled out of the original data set. Do the forward propagation, calculate the input sum, activation of its neuron, the output of the linear combination by iteratively do the matrix vector multiplication like this. So the previous page already illustrate very clear, it clearly and taking component-wise the convolution, the transfer function of the neuron in every layer. Say the result for later, the output. When you have the output, you compare the error and use a backpropagation to perform the parameter update. and calculate the error signal of the final layer L by obtaining the gradient of the cost function with respect to the output of the network, partial error, partial output. And this expression will depend on the current training sample, input and output. That's it, as well as the chosen cost function. That's it. So, and once the batch going, so the current, I would say respect the output the current, depend on the current training sample. The sample can be divided different batches, the current sample, and accumulate those errors, take the backpropagation, calculate the error signal for the neuron in each layer, boom. Reversely, the input son of each neuron is required to do this, to achieve this, and it is also done by iterative computing matrix vector modification. Then this is backpropagation and calculate the derivative of the cost function with respect to the weight. The activation function, each neuron is required. So that's how you need to specify what kind of the activation function utilize, like a sigmoid or a hyperbolic tangent. So their derivative is well known in advance. So see the formula above, and that will be a matrix with the same shape as a wave matrix. Since the structure is fixed already, so all the shape will be can be well known, and calculate the derivative of cost function with respect to bias. So then that can be only the one column vector, B1, B2, B3, only one column. So update the weights since all the parameters, what the weight should be, since with respect to the part should be going to be, the coefficient is equal to 1 according to the delta. Update the weight, and the delta could be the moment only, could be the first moment only, second moment, or use the atom or the corrected atom rule. So there's several case studies, so I won't go into details one by one. This is LabNet. This is a first one successful application of convolutional network was developed by the Young LeCun 1990. Of this, the best known is the LabNet architecture that was used to read the zip code digit, and well, it's quite easy for the classify. AlexNet, this first work that popularized convolutional networks in computer vision as AlexNet, developed by the Alex Krizavsky, the Ilya Sutskever used to work in the OpenAI. The Ilya Sutskever and the Jeffrey Hinton. The AlexNet was submitted to the ImageNet. The ImageNet is a pioneer work. And iOS VRC, the conference challenge in the 2012, and significantly outperformed the second runner-up, top 5 error of the 16% compared running up with a 26%. So average is 60% better than the top 5. Yeah, the network and the network had a very similar architecture to the net, but was a deeper, bigger, and feature convolution. No layers stack up on the top of each other. So previously, what is common only have a one single convolution layer, always immediately followed by a pooling layer. And later, there's a DFNet. which was also a convolution layer from the Matthew Ziller and the Fergus. It became well known as the ZFNet, and the Google LeNet. So it's also known as the inception module that dramatically reduce the number of parameters in the network from the 4 million compared to net with 16 million. Additionally, this paper uses average pooling instead of the max pooling instead of the fully connected layer at the top of the convolution net, eliminating a large number of parameters that do not seem to matter that much. And VGG, this is very well known back in the 2014, was the network from Karen Simon Yan and Andrew Zimmerman that become well known, the VGG. And a main contribution was in showing that the depth of network is a crucial component for good performance. So it could have some mediocre depth or very deep architecture. The final best known contains 6 convolution fully connected layer VGG16. Appealing features extremely homogeneous architecture that only perform 3x3 convolution, 2x2 for the pooling. That's good enough from the beginning to 10 until the end. So the downside of VGGNet is that it is more expensive to evaluate and use a lot more memory parameters, over 140 million. Residual net is a genius work by Kai-Ming He, who worked as AI expertise for the Microsoft, was a winner IL to skip connection and heavy use of the batch normalization. The architecture is also missing fully connected layer at the end of the network. Residual nets are currently by far state of the art. Yeah, for many cases, convolution neural network models are the default choice for using convnets in practice. In particular, also see more recent developments that tweak the original architecture from He Kai-Ming. So there's some additional information. So no for residual nets. So so this is residual. Sometimes this f of x. So we would not directly tackle the h of the x itself. Then we just estimate the f of x. Then we use f of x, the compute as the residual of the h of x minus x. And so like this is a ReLU, and then this is a residual block, which also use in a transformer. So ReLU f of x plus x, the ReLU, and this is x directly to identify x and the subtract h of x, subtracts, and then f of x can be estimated. This is residual. Identify x and h of x. So this h of x minus x is f of x. So if the number of the channel C of the x does not match the final output of the last convolution layer, and the 1-by-1 convolution with the C filter must be applied to the x. So this is like an adjustment term. And the inception, so this is quite okay. So I leave it at the personal reading. This is almost 10 years ago. So the filter was multiple sites on the same level. So this is inception. So large kernel size for information distributed more globally, small kernel size for information distributed more locally. And this inception user trial 1 in the polling layer as well. The dense net, the user not called a skip connection. So for the dense net, you can the dense net connect each layer to the remaining layer in the feeding forward fashion, like X from 1 to 3 to 4, 3, 4, 5. 1 to 2, 3, 4, 5, 3 to 4, 3 to 4, 5, and 4 to 5, and so on and so forth. So feature map of the all preceding layer I use as an input, and its own feature map I use an input to all the subsequent layers. That's called the dense net. So this is complicated. The more parameter hyperparameterization need to be estimated. The combo and efficient net. So I also like 2 years ago, I also tested this efficient net, rethinking the model scaling for convolutional neural network. Efficient doesn't it is computational efficient. So model scaling based upon the width, the depth, number of layer, number of the filter, and the image size and resolution. So baseline with scaling, the depth scaling, the shrinking, the resolution scaling, compound scaling. So it's a more efficient. Sometimes when I use an empirical net to solve the wafer map problem, yeah, it can provide equivalent competitive performances in classification. The 1D CNN. So this is time series. The input layer, layer 1, layer 2, layer 3, the fully connected. So that will be addressed later. This is a more specific class on this particular topic. How can we deal with the time series temporal data? And okay, so the input multivariate time series, they can differentiate in different channel. Okay, use a different window. It can be the channel. This is due to the pattern found, due to the seasonal factor found. The remaining can be the high frequency pattern, low frequency pattern. The last one going to be the residual, the output multivariate series, the inception mode. And okay, input DNN. Okay. This is depth as you can see that the different window size 10, 20, 40, and then the combo 1D, the max polling. And okay, so this is the detail of the inception model. Okay, the inception time for the different. Okay, time series. Okay, like this, I give you some illustration. The time series CNN for the multi-preprocessing of the input signal can be original. The multi frequency can use the ICA to differentiate. So different channel, high frequency, the low frequency, do the smoothing, and this is downsampling can be contained. Take the average. So this is convolution layer, and then concatenation into to the more complex layer, and convolution plus pooling fully connected softmax and to predict. So already need to determine how long you should perform prediction. So applying pre-processing such as smoothing or Fourier wavelet transform. So you like to perform the feature engineering to extract what is embedded feature within. So like a multi-frequency or multi-scale EMD, the empirical mode decomposition of high frequency, low frequency, and the residual, or the high pass, the low pass filter, like common filter, the Gaussian filter to the original time series signal, and do the convolution to multiply together, and the low pass filter to the original time series signal, do the combo of the individual transform signal, then concatenate every one the feature map followed by the convolution layer and fully connect, and followed by the softmax. Okay, so I stop here. It's almost 11 o'clock. So that is good for me. So I know it's not that clear through the online lecturing. So I still highly recommend you read the notes, and just if you have any question, you can ask me in my class. Thank you.